Hello, welcome to a video on the second half of section 8.2 regarding L'Hopital's rule. So here we are near the bottom of page 3. Examples 4 and 5 were done in class. And we're going to talk about indeterminate forms that look like this, where when you plug in whatever x is approaching, you get something like 0 times infinity or infinity minus infinity. Now, we are familiar with these two that we talked about last time, and when that occurs, feel free to use L'Hopital's rule, which is simply taking the derivative of both top and bottom of your fraction. And when you can start plugging in what x is approaching, of course do so, and you get your limit. Now, when you do see, again, something like this happening, 0 times infinity or infinity minus infinity, well, of course, infinity plus infinity is infinity. 0 over anything is, of course, 0, right? But infinity over 0 can be kind of funky. Could be positive infinity or negative infinity, so it's a bit ambiguous. But really, I'm more interested in these two forms. And if we're a little cunning with our algebra, we could get this to work out so that we do get 0, 0, infinity, infinity falling out, and then apply L'Hopital's rule. So we're going to have to be a little creative here. So let's look at example 6. Now, in this case, x is approaching negative infinity, so if you were to plug in whatever x is approaching, it's negative infinity times sine over 1 over negative infinity. So that's just basically negative infinity times 0, because this is, of course, approaching 0. So how can we get creative about this one problem? Say we let w equal 1 over x. If we do that, then we have the limit as x approaches negative infinity of 1 over w times sine w. Or it's the same thing as saying the limit as x approaches negative infinity of sine w over w. So again, if w equals 1 over x, then x equals 1 over w. And of course, that's going to be w itself. Now, this is a limit that we should be... actually, no, I was thinking of another scenario. Actually, another mistake I just made. My apologies. So, of course, if we're changing from x to 1 over w, we've got to change this as well. Sorry about that. So, if x is approaching negative infinity, then w, of course, has to be approaching 0 from the left. Mainly because, again, you would need w to be getting close to 0 if you want x to be going towards negative infinity. And, of course, you want w approaching 0 from the left. If you think about it again, 1 over negative infinity is basically close to 0 from the left. So my apologies I didn't switch that. So we have this. Okay, so now we got sine w over w, which of course is an indeterminate form, 0 over 0, as w is approaching 0 from the left. Now, I can apply L'Hopital's rule. Which is cosine w over 1. And of course, we just get 1 in this case. So that worked out very nicely. Again, my apologies about that mistake. So we let w equal 1 over x. So that means x is 1 over w. We substitute, but I forgot to substitute for what our variable is approaching, because now we're doing in terms of w, not x. So I had to change x going to infinity from w approaching 0 from the left. And then, of course, we can apply L'Hopital's when we're good. Okay, for example 7, it may help to rewrite this fraction, because right now, if I do plug in 1, I get 1 over natural log of 1 minus 1 over 1 minus 1. That's basically 1 over 0 minus 1 over 0. That's not indeterminate. So we can't apply L'Hopital's rule yet to the way this expression looks. We need to rearrange it so that indeterminate form 0 over 0 falls out, and then we're okay. So if you see two fractions, it might be a good idea to find the least common denominator. So 1 over ln x minus 1 over x minus 1 times ln x times ln x times x minus 1 times x minus 1. So you wind up getting x minus 1 minus ln x over x minus 1 times ln x. Now, if I do plug in 1, this is what's going to happen. And we do get actually 0, 0. So now the way I've rewritten the expression I'm taking the limit of, feel free to take the derivative of both top and bottom. Where it looks like we're going to have to do a product rule at the bottom, but that's okay. You guys should be comfortable with that. Remember, we're doing top and bottom separately, so there's no quotient rule here. So that's 1 minus 0 minus 1 over x. And then using product rules, x minus 1 times 1 over x plus 1 times ln x. And I probably still can't take the limit, because I'm going to have 1 minus 1 over 1, or 1 minus 1 times 1 over 1 plus 1 times natural log of 1. You still get 0, 0. So guess what? We do the derivative again, until get this to work, as long as it's still indeterminate. And before I do it again, let me clean that up. I think that's going to be 1 minus 1 over x. And that's just going to be plain old ln x. Okay, so we do the L'Hopital's rule again. And don't get lazy, please write your limits. Limit notation, right? So that's 0, and that's going to be minus 1 over x squared. Because remember, we have x and negative 1, bring that 1 to the front, drop that x went by 1, you get that. For the bottom, that's 0. Oh, actually, I lied. That's positive 1 over x squared, because you had a negative that we had to consider. So we also get that here in the bottom, and plus 1 over x. Okay, now I can plug 1 in, and I wind up just getting 1/2. So that actually worked out pretty nicely too. But again, you have to get a little bit creative. There are other indeterminate forms, like 1 to infinity, 0 to 0, infinity 0. They're often dealt with by taking logs before taking a limit and then converting back to exponential form. We don't do these, but I guess they are fun. Perhaps you could do them when you're in college, so we won't talk about that. But for now, let's focus on 0 to 0, infinity to infinity. And always check to make sure that happens. And remember, it doesn't always work if you're not indeterminate. Like this would not be indeterminate, right? If you just plug in, then great. Your limit's done. That's your answer. But if you try doing L'Hopital's rule, notice you'll get a different answer, right? If I took the derivative, I get 2x over 3x, which would be 2/3. So remember, it fails if 0, 0 or infinity doesn't occur at the start. Some additional notes. Some multiple choice problems, students will know that as x approaching infinity, that this tends to be true. That even though natural log of x is approaching infinity when x is approaching infinity, or something to the x power, or even x to the x power, the things that natural log of x moves slowly, as x approaches infinity, b to the x increases quickly when x approaches infinity. That's because ln x looks like this, and b to the x looks like this. X to x is a really strange one. That's just a really quickly moving function. X to the x quickly increases. And we have suspicion that the College Board might be putting some problems like that, so we want to have a discussion that maybe when I'm back next week. X to x quickly increases when x approaches infinity. And p of x is just some polynomial, like x some power. That also increases quickly, but not as quickly as b to the x or x to the x. And the double inequality signs just means like way smaller, in case you're curious, or way bigger. Now, in the case of example 8, we're just going to say that's 0. That's because e to the 0.5x increases more quickly. Sorry, I'm kind of squeezing that in there. But compared to x cubed or 7x, those are part of a polynomial. E to the 0.5x will increase more quickly than x cubed or 7x as x approaching infinity. So basically the bottom is getting bigger more quickly than the top. So that's why, for example, it would just get 0. Now in this case, because we have two polynomials, we kind of just look at the leading terms. 14x squared plus dot dot dot, negative 15x squared plus dot dot dot. So that's just 14 over negative 14/15. And again, being a little lazy, we kind of write the limit notation. Or here, we kind of know that's 0 because the degree of the numerator is less than the degree of the denominator, so we expect the polynomial on the bottom to be increasing more quickly than the top. Of course, if we could factor stuff out, we should. For example 12, I guess there's no example 11. You factor out x cubed, 3x squared minus 2, x cubed, 4x squared plus 7. The x cubes cancel. Now I can plug in 0, you should get negative 2/7. This is kind of weird with the exponential expressions. You could actually multiply top and bottom by 1 over 2 to the x power. instead of doing L'Hopital's rule. And then as x is approaching infinity, we know that 5 to the 2x goes towards 0. The 1 to the 2x also goes towards 0, so you just get negative 1 in this case. We also learned about techniques that involve radical conjugates. We know about the ones with sine x over x, and it's approaching 1 or 0 if x approaching 0 or positive or negative infinity respectively. We know about horizontal asymptotes as x approaching positive or negative infinity. Vertical asymptotes, the limits going towards positive or negative infinity as you get closer to vertical asymptotes. That's why they're called infinite discontinuities. It's okay to write D&E if the limit does not exist, if your limit has to be approaching positive or negative infinity. So we'll have more of a discussion on this next week. But just a reminder that you can use other techniques besides L'Hopital's rule if you decide to go that route. So there is a worksheet on the last page that you'll do in class. And then there's an AP-style packet in the back of the room, and also sent as an email. And yeah, I think that's it. Okay, well, have a nice weekend. Enjoy the Final Four if you are into basketball. And spring break is just a week away. Okay, goodbye.